Good afternoon. I'm Norman Wahlberger. Today we're going to be talking about calculus. It's the 9th lecture in this series on the history of mathematics. So although the main players are Newton and Leibniz, there are quite a lot of other people who contributed to the development of calculus as we know it. In this period of essentially the 17th century. So we'll then mention a few people here and their dates. Cavalieri, 1598 to 1647. We've already talked about Pierre Fermat, very important figure, 1601 to 1665. John Wallis, 1616 to 1703. Isaac Barrow, 1630 to 1677. James Gregory, 1638 to 1675. Isaac Newton, 1642 to 1727. And Gottfried Leibniz, 1646 to 1716. I probably should also include Descartes, 1596 to 1650. So as we've talked about before, calculus has its origins really with the work of Archimedes. Archimedes investigated both the main types of problems that the calculus deals with. So those problems are really of two kinds. One are problems of tangents to curves, and the other one is problem of areas or volumes of regions. And we've seen that Archimedes was interested in certainly in areas and volumes. He was also probably one of the first to investigate tangents. He studied the tangents of his spiral. And it's these two problems that give rise to the two sort of branches of calculus historically. Tangent one gives rise to the what's called the differential calculus. And the question of areas and volumes gives rise to the integral calculus. And one of the achievements of the 17th century mathematicians was to make both of these very computational. So to generalize dramatically the kinds of problems that Archimedes was able to do, to extend this to a wide range of problems using the algebraic setup and the Cartesian setup that had been introduced by Descartes. And then ultimately it became clear through the work of quite a few of these people that the differential calculus and the integral calculus were somehow opposites or inverse problems that were directly connected. So I'm going to talk about various results here, and I'm not always going to attribute things perhaps exactly to these people. So a lot of these people contributed. Leibniz and Newton are usually given the most credit. They're usually talked about as the founders of calculus, but all of these people really contributed in important ways. So let's start with Fermat and Descartes. And the first of our problems concerning tangents. So these days we think of having a function, and we think of having x and y axes, and the function's values defining a graph, y equals f of x. So f is some function of x. And both Fermat and Descartes investigated various aspects of tangents. So if we have a point on the curve, tangent is just a line approximating the curve at that point. That's a tangent. And there's a notion of the slope of the tangent. So if we just take any 2 points on that tangent and draw lines parallel to the axes, then we have a little displacement here, dx, a little displacement dy there, and then the slope of the tangent is this ratio dy over dx. And in terms of that notion, Fermat realized that maxima and minima problems really came down to the problem of when is a tangent horizontal. So he realized that, for example, if we want to find this local maximum of the function, that's exactly the place where the tangent is horizontal. Or this place here, it's a local minimum, another place where the tangent is horizontal. So this was Fermat's insights that max and min correspond to horizontal tangents. i.e. where the slope is equal to 0. And in the 17th century, people dealt a lot with small increments, or little increments, which were often infinitesimal. Things like dx and dy, they played a kind of notorious role in the history because they were at once both very useful idea but also a little bit problematic logically, and people didn't know exactly how to deal with them, but they did talk a lot and use them quite effectively. So roughly speaking, they thought of dx and dy as being small but very small little increments that were pretty close to 0 but maybe not quite 0. So the way they would have used this is, for example, in analyzing a function. So let's take an example. Function y equals x cubed plus 2x. So we can think of that as a function of x if we like. And it has some curve associated to it. Perhaps like, well, it's almost like x cubed, but maybe a little bit bigger. So something like that. And suppose that we have a point on the curve. So let's denote that by x0, y0. That's a point satisfying the equation of the curve. And the way they would have analyzed this is to make an infinitesimal analysis. He would have said something like, well, f of x0 plus dx. If we move from x0 some small amount dx, then what happens? Well, in this case, it would be x0 plus dx all cubed plus 2 times x0 plus dx. And they would have used ordinary algebraic manipulation with these infinitesimal kinds of quantities. So they would have used the binomial theorem to expand this, write it as x0 cubed plus 3x0 squared times dx plus 3x0 times dx squared plus dx cubed. That's the first term. And the second term, 2x0 plus 2 dx. And then they reasoned, well, if dx is a very small quantity, then dx squared is a super duper small quantity, and dx cubed is even smaller. So we can basically almost ignore, well, we can ignore those, and then we get something that's much simpler. So it's really just x0 cubed plus 2x0 plus the dx part. We'll just have these two terms, 3x0 squared plus 2 dx. And the way they would have interpreted that is to say, well, this is the function's value right here. That's the function at the point x0. There's the function at some neighboring point. So the difference between these two things, dy, which is sort of f of x0 plus dx minus f of x0, the difference between those is just this extra term here, which is 3x0 squared plus 2 times dx. And this is then a relation between the small change in x, dx, and the corresponding change in y, dy. So that would be the point y0 right there. There's x0 down there. We're changing x0 by dx, changing y0 by dy, and the relationship between dx and dy is given by this expression here. Well, these days we like to rewrite this in terms of a derivative. So these days, when you learn the differential calculus, it's not really about differentials. It's really about derivatives. But back in the days when calculus was first invented, differential calculus was really about differentials. It was really about statements like this, which these days we write simply as dy dx. Well, simply, we just rewrite it as dy dx would be 3x0 squared plus 2. Which I hope you recognize is the derivative of that function. But although we generally use the apparatus of limits and so on to define the derivative, the early pioneers just worked with the algebra of differentials. They were able to do quite a lot of good things. And they were able to not just analyze functions in the plane, things of the form y equals f of x. They realized that's actually just a rather special kind of curve. A more general curve might be something given by, say, a polynomial in x and y. Okay, this is just a special case when you have the polynomial y minus f of x equals 0. More general curves can also be treated with these calculus ideas, and they derived, for example, the following relation, that if you have a point x0, y0 satisfying such a curve, and you're interested in the tangent at that point and its slope, that dy dx is equal to minus the partial of p with respect to x divided by the partial of p with respect to y. So to give an example of that, for example, suppose that we're dealing with the most fundamental curve, which is that of a circle, with the equation x squared plus y squared equals 1. Suppose we have a point on it, say a point right here, maybe point 3/5, 4/5. That's a point on the curve. And suppose we want to know what is the tangent or the slope of the tangent at that circle. Well, I suspect that most calculus students these days would say, well, we have to first solve for y as a function of x. We have to look at y equals square root of 1 minus x squared and then do some differentiation involving square root of 1 minus x squared. But this formula here, well, we just apply it to this situation here where the polynomial in question is x squared plus y squared minus 1. And so then the derivative dy dx is, according to this, it's going to be minus the partial of p with respect to x. That means we're just differentiating it with respect to x. That's 2x. And then divided by the partial with respect to y. So we just differentiate it with respect to y. And we get minus xy. And when x is 3/5 and y is 4/5, that will be minus 3/4. So that's the slope at the tangent at that point. Just a very simple example of that formula. If we go back in time to the ancient Greeks and we look at Archimedes' work, we see that Archimedes was very interested in areas and volumes, but only marginally interested in tangents. And that's pretty well the case also in the 17th century. Although tangents have some use, for example, to calculate maxima and minima, all of the really important problems of calculus are problems of integration. They're problems of calculating areas and volumes. And so the balance between differential calculus and integral calculus is kind of lopsided. The integral calculus is in fact much more important really in terms of applications. And that's where most of the work went in, to try to understand areas and volumes in some kind of general way. All right. So let's turn our attention to that, areas and volumes. Well, there's one formula that dominates this branch of calculus, and it's this formula here, that the integral from 0 to 1 of x to the n dx is 1 over n plus 1. Or slightly more generally, if we integrate from 0 to a of x to the n dx, we get a to the n plus 1 over n plus 1. Actually, kind of a scaling argument. A change of variables means that once you know this one's not too hard to find. So it's really this formula that's a key formula for integration. The area underneath the simple function x to the n. Well, such a function is like a parabola. Okay. And the case of the parabola goes back to Archimedes. So basically Archimedes knew this integral when he worked with the parabola, and he knew that it came down to a certain series, that ultimately you were interested in this area, and it was natural to break it up into little rectangles, and then if you analyzed all these rectangles, eventually you had to add them up, and you got a certain series that you had to sum. And this series is essentially the series of all the squares up to k squared. And Archimedes knew what that series summed to. It sums to k times k plus 1 times 2k plus 1 all over 6, which is roughly k cubed over 3 plus lower order terms. So if we ignore the terms lower in degree k, the top term is k cubed over 3, and that's what really ends up driving the integral to be 1/3. Well, the 17th century people also realized this, that it was important to sum this kind of sum, and that if for higher powers of n, you needed to sum or to get some control over sums like this with higher powers. For example, things like 1 plus cubed plus 2 cubed plus 3 cubed and so on up to k cubed. This is another interesting sum, which is a lot like, turns out it's exactly the same as the sum 1 plus 2 plus all the way up to k, all squared. It's a rather remarkable fact. And 1 plus 2 plus all the way up to k is the same as k times k plus 1 over 2. So this one is all of this squared. And if we just take the highest order terms, we're getting k to the 4th over 4, and then plus lower order terms. Again, we can see that the integral being 1/4 appearing from that sum. Well, this sum is a little bit more challenging as these exponents get bigger, and it becomes a little bit tricky to find closed form expressions for these things. It was eventually done, but a little bit only later. But people found indirect ways of calculating these integrals, and it was Cavalieri who first established this formula. Cavalieri established this formula not by using such a series, but rather by some tricky transformation arguments involving the actual curves. But he wasn't able to prove it for all n. He was only able to prove it for n equals 1 up to 9. So he had separate argument for each degree. And then later on, Fermat and Descartes and Roberval came along and established this result in generality for general n. Cavalieri is also known for kind of a principle that was applied in a wide variety of situations that allows one to analyze areas and volumes too, and he called it the method of indivisibles. So, just to give a very simple example of it, suppose that we have a triangle here with some base d, and we have another triangle over here with also a base d, but it's sort of slightly different. So these heights are the same. Then the way Cavalieri thought about an area like this was as a lot of little infinitesimally thin line segments all stacked together. And by thinking this way, he could compare all the line segments stacked here with the ones stacked there. It's not too hard, for example, in this case, to see that if you draw a line parallel to the base here, that this line segment here is necessarily the same length as that line segment, just by similar triangles. So the fact that this segment was the same as this segment, and that was true for any parallel line, allowed Cavalieri to conclude that in such a situation the area of this must be equal to the area of this, because all the little cross sections are the same. And he applied this kind of reasoning to more fancy things. In particular, he was able to calculate the volume of a sphere, going back also to Archimedes, in a nicer, more obvious way than Archimedes had done. And it was a powerful idea, and it turns out that once people discovered Archimedes' method, which was only discovered in the beginning of the 20th century, that this was not too far from Archimedes' point of view as well. He also thought of dividing things up into lots of infinitesimal little strips. Okay, so once people had this fundamental formula here for integer values of n, typically, first n equals 1, 2, 3, 4, and so on. They also thought about variance. For example, what about fractional powers? So suppose we're interested in the integral from 0 to 1 of the square root of x dx. That's the case of our formula where n is equal to a half. Well, it turns out that the formula still works. So with x equal n equals a half, we would get 1 over 1/2 plus 1, which is 2/3. And one way of reasoning, of establishing this, is to think geometrically. So here is 0 and 1 and 1. And to start off with the function y equals x squared. The function y equals x squared, well, we know what the area under that is because that's the formula that we already know. So we know that this is 1/3. And then you realize that when you're looking at the square root of x, the picture is a lot the same. except that instead of going up like this, the square root function looks like this. So there's y equals square root of x. In fact, it's just the reflection of this one along this diagonal. So if this one is equal to 1/3, that means that this must be equal to 1/3 by symmetry. And so this one, because the whole square is 1, this one has to be 2/3. So you could then find the integrals of fractional powers in this rather direct geometrical way. So this extends the formula, extends our basic result to fractional powers. John Wallis discovered some lovely formulas due to pi. So pi, of course, had been a source of fascination to mathematicians for a long time. We've seen Archimedes think about pi. We've seen with the Arab mathematicians, the Hindus, the Chinese. Everybody was interested in what is pi, what's a good formula for it, what's a good approximation for it. So Wallis found a rather remarkable formula as an infinite product, very unusual kind of thing. So it says pi by 4 is 2/3 times 4/3 times 4/5 times 6/5 times 6/7, and you keep going. So after this, the numerators are all even numbers in pairs, 4, 6, 8, 10, and the denominators are all the odd numbers in pairs, 2 3s, 2 5s, 2 7s, and so on. And as you get closer and further and further on, these numbers approach 1. So what happens if you take products? Well, you start stabilizing towards some particular value. So if you compute the first 10 values, you get an approximation to pi. And if you compute the first 20 values, you get a better approximation, and so on. It was a rather remarkable formula at the time. Another formula that was discovered was a continued fraction formula for not pi over 4, but actually the reciprocal of pi over 4. And that continued fraction was this: 1 plus 1 squared over 2 plus 3 squared over 2 plus 5 squared over 2 plus 7 squared over 2 plus, and so on. It's not exactly the kind of continued fraction we've talked about earlier. It's a kind of a modified continued fractions where these numerators that are appearing here are allowed to be something different from 1. But it's still very regular. All 2's here, and here just all the odd numbers. The actual continued fraction for pi is very irregular, and it's very hard to know what the pattern is. Here the pattern is completely given, and so we know exactly how it continues, and we get this really remarkable formula. In fact, it was a sort of a glorious age. People were discovering these formulas, and they were all very excited by these formulas that they discovered, and they would exchange letters. And I think it was a time of they really knew that they were in the great new world, and there was they had these tools to discover these fabulous new things. I probably should also mention another formula for pi, which 1 minus 1/3 plus 1/5 minus 1/7, and so on, that you're probably all familiar with. Okay, so now we come to the two main figures, to Newton and Gregory. Not Newton and Leibniz. Gregory is also important, but so Newton, brilliant physicist, great mathematician, rather exotic character who later on in his life became interested in all kinds of religious things and was master of the London Mint for many years. and certainly made a name for himself with his great work, the Principia, which laid out laws of motion. We'll talk more about that. That was absolutely fundamental work in modern physics, laying the groundwork really for the modern technological age. But he also made important contributions to mathematics, and in particular to calculus. So he was, with Leibniz, he's usually considered one of the co-inventors or co-discoverers of calculus. Now, Newton's thinking was characterized by certain ideas. So I would say that, first of all, he had a very dynamic view of things. And by that I mean he was a physicist, okay, and he thought about things moving. So for him, time was somehow behind all kinds of functions. When you had a function, it was really expressing the movement of something with respect to time. So he was very interested in the interpretations having to do with velocity and acceleration and distance, because that naturally fitted with his work in physics. The other very important characteristic is that he had a love of series. And he was really the originator of what are now called power series, which are a main tool for analysis. And I'll give you a quote of Newton's from Stilwell. Newton in 1671, he writes the following: "Since the operations of computing in numbers and with variables are closely similar, I am amazed that it has occurred to no one, if you accept N. Mercator with his quadrature of the hyperbola, to fit the doctrine recently established for decimal numbers in similar fashion to variables, especially since the way is then open to more striking consequences. For since this doctrine in species has the same relation to algebra that the doctrine in decimal numbers has to common arithmetic, its operations of addition, subtraction, multiplication, division, and root extraction may be easily learnt from the latters." What Newton is referring to here is that not too long ago, people had become familiar with the Hindu Arabic number system, and they knew that it was nice to deal with infinite decimals, or at least decimals that carry on. For example, pi. Okay, and I remind you what this really means. This is 3 plus 1 times 1/10 plus 4 times 1/10 squared plus 1 times 1/10 cubed plus 5 times 1/10 to the 4th, and so on. And Newton said, all right, well, what's really going on here? When we're learning to do arithmetic with these decimals, what we're really doing is we're learning to deal with powers of 1/10. That's what it amounts to. And what's so special about 1/10? We could just as well consider, so slightly more generally, said, why don't we consider things of the form a0 plus a1x plus a2x squared plus a3x cubed, and so on, where the x is not necessarily 1/10, but perhaps something else, or maybe just a variable. And his point that he's making here is that if you know how to do arithmetic with these kind of decimals, then you automatically know how to do arithmetic with these kinds of things, because you multiply them in exactly essentially the same way as you multiply decimals. You add them, you divide them the same way. He even says that you can extract roots, like a square root, in the same kind of way. So for Newton, something like this was really an infinite polynomial. And to him, this was what a function was. A function was an infinite polynomial. So there were polynomials, and then you went further, and then you got infinite polynomials, which are functions. And that's basically what analysis is about. So as far as Newton was concerned, the formulas for derivatives and the formulas for integrals really just amounted to two formulas. All what you really needed to know was that the derivative of x to the n is nx to the n minus 1, and that the integral of x to the n is x to the n plus 1 over n plus 1. And then you could differentiate and integrate any series whatsoever. You didn't need to know really anything any more than that. But you had to have some skill with the algebra of these infinite polynomials, and Newton had quite some considerable skill with them. And I think it's really the introduction of these kind of series into mathematics that really distinguishes this century and opens up so many new directions. So, for example, some examples of series that are important. Well, perhaps the most important series is the geometric series, which tells us that 1 over 1 minus x is 1 plus x squared plus x cubed, and so on. Now, strictly speaking, these days we would say, all right, this is only valid when x is less than 1. Otherwise, it doesn't converge. But in those days, this kind of fussing around was not necessary. We just talked about this thing as a function, and we didn't worry too much about its values at particular points and whether they converged or not. So, for example, if you want 1 over 1 plus x, it's a small modification. You just replace x with minus x, and you get an alternating series like this. And then if you want to integrate, let's say we integrate 1 over 1 plus t dt from 0 to x. Well, then we're basically just integrating this thing here. 1 minus t plus t squared minus t cubed, and so on, dt. And so we can apply the fact that we know what the integral of any one power is, and then we just get x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, and so on. And this was the quadrature of the hyperbola that he's referring to, of Mercator. This is a very important problem because it fills a gap that our basic formula left out. So our basic formula was integral of x to the n dx from, say, 0 to 1 is 1 over n plus 1. But there's obviously a problem if n is equal to minus 1. Okay. So for n equals minus 1, there is a problem. N equals minus 1 is the function 1 over x. So here's the function 1 over x. It goes through 1, 1. As y equals 1 over x. Okay, so integrating the area under here, we don't have a formula for it. They didn't have a formula for it, but Mercator's formula, this one here, really provides an answer. And although it looks a little bit different because instead of having 1 on t, we have 1 over 1 plus t. The effect of which is to shift it by 1 to the left. So if I shift this 1 to the left, I get this. Then we'll have an asymptote here, and it will look like this. Okay, so in yellow here, this is the function y equals 1 over 1 plus x. And this now is a nice function at 0. It's right there. And we can then try to integrate it. And that's exactly what this formula is doing. It's giving us the integral of this function. which is a new function that people hadn't seen before. Obviously it has to start at 0, and it kind of goes up like that. You can extend the integral by going to the negative values as well, and you get negative values here. And what is this function? Well, these days it's what we call log or ln of 1 plus x. And if we translated it over 1, I'll just do it here. Coming down like that. That would be just to translate this thing over. That would be log of x. So this can be taken as the definition of what the log function is. It's what you get when you try to integrate the one case that the Cavalieri's formula doesn't work for. You get a new function, you have to throw it into your tool chest, and of course that enriches the subject quite a lot, because then the inverse function is the exponential and so on. And this is the kind of thing that Newton loved doing. He would say things like, okay, so let's call this y. So let's say y equals x, or x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 and so on. Can we write x as a function of y? How do you invert this? How do you write x as a function of y? Well, what he did is a rather clever thing. He said, well, what we'll do is we'll suppose that x is also a power series in y, but the coefficients we don't know yet. So we'll let them be unknowns, perhaps a0 plus a1y plus a2y squared and so on. And then we'll plug that into here. Now we've got a lot of big algebra to do, because we have to take that thing there, and then we have to square it, and we have to cube it, and we have to take the 4th power and then combine them all and see what we get. And then we're going to compare coefficients. On the left-hand side we just have y. On the right-hand side we have this whole bunch of stuff. With any luck we can deduce what these values must be. And in fact, it's a great exercise. You can do that. What he found is that you get a series which is 1 plus y squared over 2 factorial plus y cubed over 3 factorial and so on. Now I may not have done that quite correctly, because this is ln of 1 plus x. Yeah, okay, that's not quite right. If y equals ln of 1 plus x, then what should x be? Then 1 plus x should be equal to e to the y. And so x should be equal to e to the y minus 1. So the series that he would actually have gotten wouldn't have this 1 here. That's the series for e to the y that I was starting to write there. That's better. Okay, so we now call that, well, without the 1, that's e to the y minus 1. Because I happen to have inverted this one here. So in high schools these days, you often start with the exponential function. You define the exponential function through some geometrical series, and then you take the inverse function to find the log. But it's mathematically more natural, as the 17th century mathematicians realized, to define the log first. The log is essentially coming from integrating 1 over x, and then inverting the log function to get the exponential. Well, Newton was an expert at this kind of thing, and he did lots of other things like that. And one of the most important things that he thought about was the binomial series which was a key tool in other things. And after the geometrical series, it's probably the next most important series, so the binomial series. Well, you're probably familiar with expansion of 1 plus a to the n as 1 plus n choose 1 times a plus n choose 2 times a squared, and so on, up to some limiting value, some final value of a to the n with binomial coefficients. But these binomial coefficients can be rewritten as 1 plus na plus n times n minus 1 over 2 times a squared. And then the next one, n times n minus 1 times n minus 2 all over 3 factorial times a cubed. And then, in fact, there's no need for us to restrict to integer positive integer values of n. If n is a positive integer, like 5, then this series will eventually stop, because you'll eventually get to n minus 5. But if n is not a positive integer, this gives an infinite series. Particularly important is this one, the series for 1 plus a to the half, well, which starts off as 1 plus a half a plus a half times minus a half over 2 a squared, and so on, and it just keeps on going. So binomial theorem, that binomial series, that was one of Newton's favorite tools, and he used it to investigate the circular functions. Sine and cosine, which of course going back to antiquity, but he analyzed them algebraically in this sort of power series point of view. And how he did it was rather interesting. He started with something which is essentially it's something like this. So the arc sine, if you define this to be the integral of square root of 1 minus t squared dt. Okay. So what you can do then is you can think of this as being a special case of this more general thing here. So you can rewrite this as 0x 1 minus t squared to the minus a half dt. And then you can apply this kind of binomial series to 1 minus t squared to the minus a half and expand that out as a series. Once you've expanded it out as a series, you can integrate it term by term. So Newton, integration meant you expand it out as a series and then you integrate term by term because you know what the integral of x to the n is. That's all what you need to know. He didn't think in terms of various rules for integration. There was only one rule for integration. That was the integral of x to the n is what it is, x to the n plus 1 over n plus 1. So his strategy would always be to evaluate everything as a power series first and then integrate, and the integration is relatively trivial. So what you get when you do this is this series, x plus 1/2 x cubed over 3 plus 1 times 3 over 2 times 4 x to the 5 over 5 plus 1 times 3 times 5 over 2 times 4 times 6 x to the 7 over 7, and so on. Now that's a much less well-known formula than the formula for the power series of sine of x. I suspect many of you will know the formula for sine of x, but perhaps this one, maybe you'll have seen it, but you probably can't remember it. I'm like that too. But it's rather remarkable that Newton discovered this one first and then used it to find the value, the power series for sine x. Okay, he didn't know what the power series for sine x was. He found it by a lot of work after he got this one. So basically he said, all right, suppose that y is equal to sine inverse of x, which is just that thing there. Then, okay, then sine of y is equal to x. So how do we write sine of y? Well, we have to invert. We have to take y equals this formula, x plus 1/2 x cubed over 3, etc., blah, blah, blah. We're calling that y. And now we have to solve for x in terms of y. How do you solve for x in terms of y? Well, you have to let x be a power series in y with undetermined coefficients, just like we did before. You have to plug in. Each one of these is going to become a series. You have to do a lot of algebra. Eventually, you find out that sine of y is, what is it? It's y minus y cubed over 3 factorial plus y to the 5th over 5 factorial minus y to the 7th over 7 factorial, and so on. And you can imagine his excitement when the smoke clears, all the algebra somehow becomes dramatically simple, and instead of getting something incredibly complicated, you get this pretty pleasant formula. Okay. But it turns out that Newton was not the first to have discovered that formula. Okay. It turns out that these formulas for arc sine, they actually go back to Indian mathematicians. In Kerala, in the southern province of India. Kerala, I think, yeah. At least 100 years, maybe a couple hundred years before Newton. Not way long back, but a couple hundred years before Newton. They were very interested in astronomy, and they had very sophisticated mathematics. Okay, so that was Newton, and now let's say a few words about Leibniz, who was a German mathematician who also shares credit with Newton in the discovery of the calculus. And unfortunately, there was quite a big bickering between Newton and, well, not between Newton and Leibniz, but then also between the followers of Newton and the followers of Leibniz. And it soured relations between the British mathematicians and continental mathematicians for quite a while. And in fact, it also set back the British mathematicians, to be honest, in a serious way. So Leibniz did not have the power of Newton, but he thought long and hard about notation. And it's remarkable that the notation that we use in calculus in the year 2011 is basically Leibniz's notation. Okay, so he introduced this sign for sum. Well, it was kind of an extended, it's a S, like a German S for sum as an integral. And he introduced this notion of dx as an infinitesimal. And his orientation to calculus was quite different from Newton's. So Leibniz was interested in closed forms. So we get from him and from his followers the familiar formulas for integration by parts, by substitution. And the way Leibniz thought about this is in terms of sums and differences. So here is some function. He thought of adding up a lot of little intervals to form a big area. And his he was thinking that this is some kind of analogous to a more discrete kind of summation difference calculus. So for example, suppose you have a series 1, 2, 3, 4, 5. That's just a series, or a sequence, perhaps we should say. Then what you can do is you can form the sums. 1, 3, add one, then add the next one, 6, 10, 15. This is a series of sums that you get by summing the original sequence. Okay. So that's sort of one operation. To go from the sequence to this sequence, you take sums. But he realized that if you wanted to go backwards, you take differences. Okay. To go backwards, you take differences. In other words, if you wanted to recover the 5, you just look at the 10 and the 15 and you take the difference between those and you get the 5 back. So taking differences of a sequence and sort of summing them up are kind of inverse operations. And that was his motivating idea for his version of calculus. He was thinking that what we're doing when we're integrating is we're summing all of these things up. Yeah? And when we're taking a d of something, d to him was really a symbol for difference. So for example, he would have said that if you have some function f of x, and then you take the integral of f of x dx. Okay, there's the integral of f of x dx. It's that area under there. If you take d of that area is a lot like the sum. The difference between the d of that means sort of the final value minus the previous final value. Okay, that difference would be that rectangular thing there. Now, if the x width here was some small amount dx, then if you divide this by dx, let's put it there, you divide this difference by dx, then you're just going to get the height of that rectangle, which is f of x. And here, this is his explanation of the fundamental theorem of calculus, that if you take a function and you integrate it, and then you differentiate that, you get back the original function. Now that's the fundamental theorem of calculus. That actually was already known to people earlier than Newton and Leibniz. It was known to Barrow and I think Gregory. Okay. So there were a lot of contributors to this story. But Leibniz, after establishing his notation, sort of his point of view, he was very good at promoting it and encouraging others to use his notation. In particular, he was very good at, he got the Bernoullis, famous Swiss family of mathematicians, to adopt his thinking. And it didn't take long before everybody on the continent was thinking about calculus using the Leibniz sort of point of view. And that was very powerful because his notation was so good. It's so good that we basically still use it today. It's really remarkable that the originator of this, we haven't really improved markedly on his notation. We've changed our meanings about what the words mean a little bit and how we introduce them, but the notation is still exactly the same pretty well. Okay, so the tools were set. We now come, it's kind of a golden age of mathematics that results from this fabulous tool. So next time we'll talk about infinite series and move on to Euler's contribution and others, some of the remarkable things that people discovered with this calculus. So see you then.